Yo, what's going on, my guys? How's it going? Welcome to, I think, Thursday. Yeah, welcome to Thursday workshop times. A little bit of a different stream for you today. Not a repair, but we are going to be looking at this. This is the Synergy, let's get the model number right, WFO 2.1D. And this has been sent in to me for circuit analysis and to see if there are any changes really that I would suggest making to the circuit going forward, or any things that might impact its performance or reliability, or just things to kind of take note of that might need to be looked at. So I thought it'd be cool to live stream this process that I go through of analyzing a circuit like this and going through all of the different areas and all the different various tests that I will carry out to identify where there might be some underlying issues that that would be best to be changed. So hopefully this is entertaining and informational for you. How's it going, Bert from Miami? What's up, my friend? RTS, what's going on, my friend? 13BTR, yo, what's going on? Good to see you all here. So I'm just going to get straight into it. I'm not going to wait too long for the stream to pick up. I guess people will just jump on. And if you're watching this back after this has finished, then feel free to skip ahead a little bit if you like. But we're pretty much going to get straight into this. And they've got the thermal imaging camera as well hooked up now as well. If this is the first stream that you've caught with the thermal imager, this is my new thermal imaging cam. It is absolutely game changing. Oh, look at how well overlaid I've got that with the main cam. Yeah, this is an absolute game changer in regards to diagnosing and finding issues. It's like so responsive. It's so quick and so sharp. I absolutely love it so much. So new thermal cam up in the building for today. So let's have a look at this circuit then, shall we? What I'm going to do is actually give you the hat cam and just kind of like get you nice and up close with the hat cam so you can see exactly what this board has and what this board is. So we have a pretty typical car audio switch mode power supply. So this is the same type of power supply layout you'll see in 99.999% of car amps. It's basically the same. We've got 4 smaller transformers here, which parallel at the after rectification. So each transformer has its own pair of rectifiers, and that then parallels at the rail caps. Having multiple numbers of smaller transformers it does apparently have its benefits. I haven't tested this personally myself, but it does seem to have its benefits over like one larger transformer. So that's pretty cool to see. Also, having smaller transformers does mean that they are less susceptible to vibration damage because they have less mass and inertia. So they tend to sort of vibrate less if this was mounted to a box, for example. So that's actually quite a cool thing to see. So yeah, we've got these. We've got power supply MOSFETs. We're going to have, by the looks of it, 4 MOSFETs per transformer, 2 in push and 2 in pull. Just check that. Yeah, the audio is working fine. Yeah, so we've got 2 in push, 2 in pull per transformer. We have gate resistors. We've got 22 ohm gates there by the looks of it. I haven't checked what FETs these are yet. We'll get to that in a bit. We have some Zener diodes by the looks of it as well, just to get rid of any spikes and ringing. This isn't really needed these days. It's more of an old thing, but it's cool to see it's still there. Got a snubber network on the transformer here. Now, we have many drivers. So these are all of the power supply drive transistors. There is a whole bunch of them here. Now, in my personal opinion, this is excessive and unnecessary. It's not an issue. It's not going to cause any problems as such. But, you could drive this number of MOSFETs with a single tiny drive IC rather than having like a whole bunch of transistors here like this. I don't know what works out cheaper. Having all of these transistors and the time and stuff to fit them versus having just one SOIC 8 or something driver. But the PWM comes from this card. Now this, excuse me, This is a very generic. You'll see this exact PWM card used in like tons of amplifiers coming out of Korea, and even some out of China now. So this is using a TL494 or a KA7500, but it's the same chip, to generate the pulses for the switch mode power supply. This also controls a bit of protection circuit on pins 1, 2, 15 and 16, so you can send this into shutdown mode via external protection circuits by sending some voltage onto pin 1 or 16. Looks like we have a transistor up here for the relay. That might be that one, or it might be the one down here. There's a couple of transistors here. One of these is going to be for the relay activation, which is over here. So that's just going to prevent any turn-on pop. Basically, when Class D oscillation builds and initializes, you always get a pop just due to the inertia of the inductors. But obviously having the relay gets around that. So this is a 40 amp relay, so yeah, plenty of current availability on that one. Now we have a little, this is something which we'll get to shortly. We have a little set of a jumper here for 9 volt on off. Now what this is supposed to be low voltage protection on or off. So from what I remember, on means that there is 9 volt protection turned on. So if the voltage on the amplifier drops below 9 volts, then it will shut down and go into protect. When this is off, then the amplifier will continue to operate as low as it physically can, based on the auxiliary supply voltages still being present in the output section, etc. So yeah, this enables or disables low voltage protection. We're going to test it. I've already tested it, and it's kind of interesting, so we'll get to that in a bit. So that is the PWM card, and this is just a very generic drop-in card that you'll see on pretty much hundreds of amplifiers now. So yeah, we'll check the model of power supply FET actually just now. Let's turn the power supply off so that's not got 12 volts on it. I'm getting lots of ads. Really? I know YouTube has upped its the amount of ads it's going to serve. Guys, if you feel like there's too many ads, then let me know and I'll see if I can change something in the settings. Like I let YouTube just deal with their own ads. I don't like manually inject them because I always forget. But if you're getting too many ads, let me know and I'll reduce them. But if you're interested in this brand of thermal imaging camera, then the links are in the description. You can check them out, and there's also a discount code in there as well. I'm not sponsored to sell these or anything like that, and I actually was going to buy one, but I reached out to see if they send me one for free, which they did, and they've also given me some commission if I do put any sales forward. So I actually really like these. I think they're freaking awesome. Look, you can actually see how cold my fingers are compared to the rest of my hand, and you can also see you can see all kinds of stuff. It's crazy. You can see the IC chip inside the camera. You can see where all the electronics are inside. It's pretty cool. Anyway, I've got the green cam now. Excellent. Too many ads. Okay, wait. Just bear with me a sec. Let me just sort this out. Why is it giving you so many ads? Just bear with me a sec. Edit. Monetization. So yeah, I've put let YouTube insert mid-roll ads for you. Balance. So if I change this to conservative, hopefully that'll help. Okay, let's get back to this. So power supply MOSFETs we have, if this will focus, IRF 3205. So yeah, these are parts that have been used for like 20 years or so. Pretty stout parts and affordable as well. Cost savings could be made by using less numbers of more powerful FET, but the cost savings might not actually, it might be just more expensive to use the more expensive MOSFETs rather than just using multiples of the 3205. So I mean, these are good parts. It's good to see them here, and they look genuine as well. They don't look like fakes, which you actually you can't guarantee that these will be genuine even coming from the factory. So let's move on and have a quick look at the rectifier model. Now these rectifiers are TO220F package, so they are closed back, which means that they can't dissipate as much energy as heat to the heatsink as the open back, kind of open tab ones can, like these TO220s over here on the power supply. So let's just have a look and see what model these are. These are MUR 1640s by the looks of it. So there's a fair bit of voltage headroom in there. This won't be, won't be switching anywhere near 400 volts. These are doublers, so these have the two diodes kind of in series inside with a center tap leg. These are quite hard to come by, so from a repairability standpoint, these are a bit of a pain in the ass, but they very rarely fail. So you barely ever will need to change rectifiers ever. Now I've got a feeling we've got 8 rectifiers, which is quite a lot of rectifiers for the power that this amplifier looks like it's going to try and make. So even though these are the closed back package, which I generally wouldn't select just because they can't dissipate as much energy as heat, because we've got so many of them in parallel, they're probably not going to be needing to dissipate that much heat to the heatsink anyway. So that's not necessarily a bad thing. One thing I will notice here, and I'll point out, is that obviously on these parts we've got thermal paste because we have a hard package against the aluminium heatsink here. So obviously we need some thermal interface material to fill in the gaps, the air gaps between the materials. However, on the MOSFETs, we actually have this kind of sill pad, thermal pad stuff, and this is actually textured with the intention that the kind of texture is squishy, and it squishes in and fills in any gaps in the material of the metal and the heatsink here. It's actually not recommended to use thermal paste. Because the thermal paste just kind of gets in the way and adds another layer of interface for the heat to transfer between. So when using sill pad like this, you actually shouldn't use thermal paste. So that's just a little thing I'll mention. I'll say, hey, see if you can get them to stop using thermal paste on the sill pad here, because it actually makes the thermal transfer worse than if you just use the pad alone. But it's minor. It's not going to make any noticeable difference really. But if you're using less thermal paste per amp, that might be a little bit of a cost saving. It's really not needed when using these pads. Okay, so we have the rail capacitors here. Now we've got 4 rail capacitors, and this is a half bridge amplifier, and it has bipolar rails. So we have a positive rail and a negative rail. Pretty standard stuff. The brand of caps is Capcon. Now we don't really know the reliability or quality of these capacitors, and they will vary with batch as well. They're not like a super reputable brand, but given how long car amplifiers are sort of expected to last, these caps should be absolutely fine. There's not a huge amount of reliability testing we can do other than just to run them for like years and see how it goes. They'll be absolutely fine. They'll be up to the job. There's no issues there. And unlike with older amplifiers, rail capacitor quality with Class D amplifiers doesn't impact the sound quality. And even if it did, for subwoofer application, it's completely negligible anyway. So these will be absolutely fine. No issues there. So let's have a move on to the output section and have a look and see what we've got going on. So we have basically 2 amplifiers in parallel. So we've got 2 output inductors. So we've got 1 amplifier over here and 1 amplifier over here. And these are going to parallel after the inductors. This is kind of similar to a full bridge amplifier, but instead of the 2 amplifiers in the heatsink being in push-pull with each other like this, these 2 amplifiers are paralleled together into a single output, which is then referenced to the ground. So a half bridge amplifier, but it's actually got 2 separate channels inside that are in parallel mono rather than in bridge mono. So let's have a look at what output MOSFET model we are running here. We have TO220 package FETs again on the output side, and they're quite nicely spaced out. So let's see what we're running. We have 3 MOSFETs on the high side and 3 MOSFETs on the low side. Very nice. Okay, these are some stout parts. We've got some FDP52N20s. Yes, these are pretty nice MOSFETs. 200 volts, 52 amp continuous, but the pulse drain current is really more what we're looking at. These are relatively easy to drive as well. So they're quite powerful parts, and they're not too difficult for the drive circuit to manage. If we take a look at the drive circuit itself, let's have a look at the gate resistor real quick. Got 22 ohm gates on here as well. We've got a pull down resistor for each FET. So the pull downs are basically all just going to parallel together. And the focus on this camera is a little bit sketchy, hey? So the pull-down resistors are all going to kind of parallel together. We have, in the middle here, just kind of shoved in there, we have, that's not great. That's not really making a great thermal connection to the heatsink, is it? We have a thermistor, which is obviously going to be dealing with the thermal management, thermal protection of this. So let's just remove that. It doesn't really look like it's super well. Oh, it is quite, actually, it is quite well stuck to the heatsink. It didn't look like it was. The legs for the thermistor there are kind of very long and they've been bent up against the heatsink, but that's not a problem. They are actually heat shrunk, so you're not going to have any issues there. So that's going to be monitoring the temperature of the heatsink as to when this is going to go into thermal protect. That's cool. The drive circuit itself, this is like a baby version of the Digital Designs Z2B, Z2C, and a lot of the new Sundown Salt amplifiers use this driver board. Again, it's a generic driver card. This chip right here is an IR2184, and this is in the DIP package rather than the surface mount package. We have what is usually a pair of TL072Cs, or sometimes you have a single 72C and a 311. That's the 72C. So this one up here, I imagine, is the LM211 or LM311. All surface mount on this one as well. Now, the bigger versions of amplifiers using this driver card will use some buffer drivers. Usually in a TO220 package, they're the MC4452s or the TC4452s. Because there's obviously more parallel FETs, but obviously given this amplifier only having 3 FETs per bank on each side, and these being relatively easy to drive FETs, there's no need for any additional drive buffering. The 2184 is just doing this all by itself, and we'll check with the thermal imaging camera whether that is under any excessive strain or not, to see how hot it gets just running idle, to see how well it's driving these FETs. But yeah, pretty cool. The bootstrapping is done on the main board here as well. I think from memory we've got the bootstrap capacitor and diode for each side is, well, I can't remember where that is on these ones. Might be these. Got the bootstrap cap, so the bootstrap diode, and then the capacitor. Is it going to be this one perhaps? 50 volt 2.2? No, maybe not that one. We'll find it. I don't think it's on the driver card itself. No, I don't think it's on the drive card itself. So bootstrapping is done on the main board. When these amplifiers fail, they do tend to take out some of the diodes around the drive circuit here, but they're not usually too difficult to replace and to repair. Relatively simple Class D circuit these. Now, in terms of auxiliary supply voltages, we have linear voltage regulators, a 7812 and a 7912 over here on the heatsink. Again, fallback package components, not a problem at all. These aren't going to be really generating much heat. We have some resistors in line with them, which I have seen has caused issues in the past with different circuit designs that use a similar sort of auxiliary supply circuit to this. So we're going to test to see whether these inline resistors cause any problems. These little green inductors, these are a little bit unreliable. These are, over time, they're very fragile, and the little inductor wire inside kind of snaps, and that can cause the amplifier to have no sound and power up just fine. So generally I'd recommend against using these kind of things. But yeah, we're going to test that as well. Let's have a look. What else do we have? Okay, so actually I think the bootstrapping probably goes on over here. Yeah, I've got this one over here, this side, and this one on the other side, yeah. In terms of output filtering, we've got our output inductors here, pretty nicely seated down to the board. Not much movement on those at all. A little bit of movement on this lead here, but that is very heat shrunk, so that's not going to be too much of an issue. Yeah, I'd say this is pretty well assembled. Not going to have too many issues with the vibration damage. We have output filter section in terms of after the inductors. We've got some aluminium non-polarized capacitors here, in addition to some film capacitors, which are going to be here as well. So obviously for the inductors to work, the high frequency information through the inductor needs to see a pathway to ground in order for the low pass filter of the inductor to work. So that's going to see a route to ground through these capacitors, but obviously the low frequency element, the sine wave that you're actually wanting to listen to, doesn't see the capacitor because it's too high value. So that's cool. Then we go through, after it's been paralleled, we go through one final inductor here, which I think is just an air core inductor, and then before going to the relay. Now this 393 and an optocoupler here is probably to do with protection circuit, so we'll check that. That's probably going to be to do with the enable of the Class D activation over here when the relay is applied to the amplifier. Preamplifier circuit over here. Let's have a look what we got on the side, just out of interest. We do have a clip light, so we'll check the accuracy of the clip light. Clip, protect, and power. Gain, subsonic from 10 to 50. We'll check that that's accurate as well. Low pass filter from 35 to 250. I like seeing a nice low pass filter setting. None of this like 80 hertz minimum nonsense that you see on all the Brazilian brands. Nice that you have a really nice low pass filter to start with. Now the main and strap switch. These can go dodgy in a lot of amplifiers, but this is a nice big switch and I don't really see many of these going bad, so that's good that we have that there. Tiffany RCAs all round, nice decent build quality. TL074s in the preamp, that's going to be absolutely fine for subwoofer application, don't need anything more than that. All through-hole components as well, this is great to see. I'm honestly not a big fan of surface mount components throughout, you know, the most of the amplifier. They're just not super resilient to the harsh automotive environment that these amplifiers get used in. Yeah, we've got surface mount components on the driver cards and whatever. That's fine. Ideally, this would all be through hole as well, but having the main board be all through hole definitely is going to improve the reliability of these amps as a whole compared to having all surface mount components when used in an automotive environment, unless they're super high grade, high build quality like an Alpine or something, or surface mount quality is really high. You can get away with a sort of lower assembly quality grade through hole component board than you can with the surface mount. You know, it's going to save you a bit of money, and the components are just larger. They dissipate their heat better. I think I'd say it's just better all round really to still be using through hole components in something like this. Okay, so yeah, auxiliary supply over this side. We have one more 7812 over here, which is going to be generating the 12 volts reference to negative rail for the drive circuit to work with. That's because the drive circuit references negative rail as its ground. And we do have some shunt resistors here, which are going to be for the current sensing over current protection. So we're going to check and test the over current protection. I don't know whether my power supply will be up to the job. I can't remember what rated power these are for, what power these are rated for. But we can hopefully be able to test the calibration of the overcurrent protection on there as well. So yeah, overall so far, build quality pretty good. Not too bad at all. Component layout fine. All through hole components. I like that we have screws down the middle of the board. So there's, the board is actually pretty sturdy in here. It's not trampolining. It's not flexing, which you see a lot of the time when they don't have center supports on here. So yeah, pretty good. And the heatsink's nice and heavy. Has a good thermal mass as well. Also the chassis ground wire is capacitively coupled rather than just being directly connected. That is a huge benefit because if you accidentally touch 12 volts onto the case while you're wiring it up, if that wasn't capacitively coupled, you just burn this wire and it just lets out a load of smoke and just kind of looks kind of bad. So the fact that's capacitively coupled is very good as well. Alright, I think we're done with the little camera just now. What I want to do is power this up and just check some of the drive waves, check the kind of idle operation, see how this thing is ticking over. Jason says, what is meant by a discrete Class D circuit? So discrete Class D is where the entire Class D drive circuit is made up with discrete components, therefore individual transistors, diodes, resistors, capacitors, etc. Whereas a non-discrete Class D drive circuit would be using an IC of some kind, like a 2092, 21844S, something where the kind of drive architecture is built into a single chip, and then you just feed that with parameter resistors and capacitors to set the different modes and stuff. But discrete Class D is a pain in the arse because Class D oscillation is very, very delicate and fussy. So the exact sort of tolerances of the transistors and stuff that you're using when you design the amp and you get it perfect and you get it working just right, years later when it comes to repairing that amplifier, the transistors, the tolerances and the characteristics of those transistors, even if they're the same model, might be different enough that you can replace all the parts for brand new. It just doesn't work like it did. It just doesn't work correctly. Something's wrong, just because it's like so. It's teetering on the edge of stability with a discrete Class D like that. How's it going, Sinewave? How's it going, my friend? Good to see you here, bro. Mind blown, no thermal paste. You don't want thermal paste when you have a thermal pad that's designed to squish and fill the gaps. Adding thermal paste is just adding another layer of barrier for the heat to get through. You do want thermal paste if you have hard surface against hard surface, like the back of the TO220F package part against the heatsink. But if you've got the thermal pad that's squishy like a sill pad, then you don't want thermal paste because it actually reduces the efficiency of the thermal transfer. Caps gone, caps. I've seen them on many Corsair power supplies and they're fine. Cool, that's good to know. So we shouldn't have any problems here then going forward. Oh, that's a Synergy brand amp. I've heard real good things about them. Yeah, so far this looks like it's built pretty nicely. I'm going to get rid of this green tint. Unplug and replug the HDMI. There we go. So yeah, this actually looks and seems to be assembled pretty nicely. It's pretty heavy. I don't know what these cost. So obviously this could be a great amplifier, but if it's like 4 times the price of a Smart 3, for example, then I'd never be able to recommend it, even if it is really good. So let's power it up and just have a look at how this circuit is ticking over on idle. So let's start off with the power supply section then. I want to see whether we have a kind of soft ramp up on the duty cycle. When we power this up, so we've got 12 volts going in, hitting the remote now. A little bit of a delay. And yeah, we have duty cycle gradually building, and now the shape of that waveform is a little slanted, so that means that the duty cycle doesn't end up being particularly high. Let's have a look at the gate waveform and do that again. So this is the power supply MOSFET gate. Okay, yep, so we have nice slow ramp up, soft start. We have a nice sharp switching waveform there, which is typical for power supply switching. It's low frequency and they're easy to drive FET, so that's pretty nice. You can probably ignore some of the spikes on the scope here because I don't have a ground probe hooked up. Well, I do. It is grounded. The oscilloscope is grounded to the power supply through the ring main. So you get a little bit of noise on the scope. I just find it more convenient. So we're just looking at the wave shape. Looks absolutely fine. But as you might notice, the duty cycle is only 41.5%. That's a little bit low. In these kind of switch mode power supplies, you can get away with running the duty cycle up to about 48% with no issues at all, which will just improve the effectiveness and the efficiency of the switch mode power supply. It just means that, you know, it can pass a bit more power before it reaches saturation and reaches its limits. So yeah, increasing the duty cycle there from 41.5 to 48% would be advisable. And the way that you do that is on this driver card here, pin 4 of the TL494. At the moment, we'll still have like a little bit of voltage sitting on it, which is causing the duty cycle to be locked in there at 41%. So what I might do a bit later is have a play around and change some resistor values just to get the duty cycle finishing off there nearer to sort of 47, 48%, and that would be a bit better for this, I believe. The only time where you wouldn't necessarily want the duty cycle up that high is if the transformer and snubber network, etc., hasn't been designed particularly well, because when you start going towards higher duty, you can get big spikes on the start of this waveform here, which can cause cross conduction and just high idle current, which isn't really ideal. So we'll see whether that's the case. I doubt it. I suspect it's just this generic power supply PWM card is just set up for this low duty cycle to cater for any amp that it's going to get thrown into, but it'd be cool to reduce that, you know, to improve that a little bit, just to improve the efficiency of the power supply section. So we're going to look at the thermals in a bit. Let's have a look at the output of the transformers. With 12 volts going in, we have plus minus 75 volts worth of rail, and this is the output of the transformer secondary. Looking pretty nice and clean, as you'd expect, with a low duty cycle on the power supply FET, so no ringing or anything there, which is nice. This means that the amplifier has a low chance of sending back any kind of noise back down the power cables to any other components in the audio system, etc. So that's pretty nice to see. Keeps things nice and clean, so that's cool. But with a 20 bucks, thank you very much, my friend. That is very generous of you. Very nice. A few months ago, you helped me track down a mini SOIC for my Stetson amp. I appreciate the time you took. No problem at all, buddy. Anytime. I'm really glad that I could help, and thank you very much for the very generous donation. I hope you're doing well today, my friend. That's really kind of you. Eight rectifiers is overkill. Yeah, there's definitely a lot more rectifiers here than probably is necessary, and we'll be able to confirm that when we do some power testing to see which of the TO220 parts along the heatsink get hot the quickest first, because that will be where the bottleneck is. I doubt it's going to be the rectifiers, even though they are closed back package. Where's your scope probe grounded to? So yeah, my oscilloscope just shares a common ground with my bench power supply. So yeah, that's how it's grounded. It obviously does mean that the ground path between the measurement point and ground is quite long, so you do get a little bit of noise on the scope screen, but I'd rather have a little bit of noise that I can just mentally block out than have a ground wire hanging off my probe. If I need to measure the exact shape of a tiny voltage waveform very specifically, then I will attach a ground probe and it cleans it up. But yeah, I much prefer just having the ability to probe around without the ground wire getting in the way. All right, cool. Let's have a look at the output section now then. I just want to see what the Class D switching frequency is. Now remember, this is a subwoofer amplifier, so we don't need a particularly fast Class D switching frequency. We're going to probe the low side drain here, which I believe is one of these ones. Yeah, over here. This is the low side drain. So we're going to see whether Class D switching comes in, whether it's got like a muting circuit, to see whether it comes in after the amplifier is already built for rail. So let's take a second oscilloscope probe to measure the rail voltage. Just real quick, so channel 2 on the scope. Let's put that on the negative rail while we're here. If I can just get that kind of latched under for a minute. There we go, so we've got negative rail there. So let's just see whether that builds fully before Class D switching initializes. So power on. Yep, so we have full build to rail, and then Class D switching initializes after the rail has been built, which is good. So power off, no swing to any rails, which is great. Power on. So yeah, the muting circuit is working perfectly. Now, one thing that I want to check is to see whether the switching frequency on this amplifier is tied to the rail voltage. And this is a thing with older style Class D amplifiers. The Class D switching frequency, because it's a self-oscillating amplifier, does vary with the input voltage, which is not really ideal because the output inductors, for example, and the filter network will have a switching frequency that is optimal for its operation. And also, yeah, everything will kind of be calibrated around an ideal Class D switching frequency. And if that is not fixed, then that means that at some points at various different voltages, you're going to have suboptimal operation. So at 12 volts, we have 96 kilohertz here, Class D switching. Let's get rid of channel 2. So if we drop up to 14 volts now, yes, you can see that the Class D switching frequency has increased to 104 kilohertz. And if we drop down to 10 volts, you can see that the Class D switching frequency drops to 87 kilohertz. So the Class D switching frequency is dependent on the input voltage, which is not ideal, but it is how these amplifiers have worked for like 20 years now. And it's not an inherent problem. It's not going to cause massive unreliability. Yeah, it's just a little bit janky. It's just a little not quite ideal. It means that, obviously as you're playing the amplifier, if your voltage is dropping between 14 and 12 volts and whatever, then it means that the sample rate of that sine wave is going to be constantly variable. It's just a bit janky, it's not going to cause any huge problems. It's just kind of not really ideal. All right, excellent stuff. Now that looks like a very beautiful looking Class D switch wave. Got no ringing or anything on there. Looks very nice, nicely built. Let's have a look at the gate waveform at the MOSFET right now. Let's just zoom into that low side drive. Okay, so these are what I would call softly switched. They're not super hard switched, which is why we have a very clean looking output waveform there with no ringing, etc. You can see here that we have a little bump on the low side drive, this is where the MOSFET turns on. So actually these FETs seem to have a very low VT, which is interesting. That's cool. So the MOSFET turns on here, which is where this little spike is, and then this is the drive circuit charging the gate, and then the MOSFET is like fully on. Now the amount of current and the amount of power that the MOSFET will be able to deliver is actually dependent on the voltage on the gate reference to source. So the higher this voltage on the gate for longer means that the MOSFET will be able to produce more power. So the less slopey this is and the longer that this line is on a higher voltage for, increases the amount of power that the MOSFET can deliver whilst it is on. Now although this looks a little curvy, it is actually, you know, well, what have we got here? 2, 4, 6, well, 7 volts here. No, sorry, we'll go obviously all the way down the bottom, aren't we? We have, so like 2, 4, 6, 8, 10, 12. We've got about 12 volts worth of gate to source voltage there. And it's pretty much at the 12 volt mark for most of the on cycle. It ramps up pretty sharply here and just curves off here. So yeah, I would say that's not a problem. We don't need to we don't need to worry about changing the gate resistors too much here. The MOSFETs will be doing their have the full power potential for most of that that cycle duration there, which is not a problem. Okay, let's have a look now at the output of the inductors here. So we obviously have the input to the inductors, which can have the Class D switch wave on it. Let's go to the output of the inductors, which I believe is going to be over here. We can go on to this one right here. Let's see how much Class D remnants there is after the inductors. Let's power up again. So this is what we have remaining after the main inductors here. We have a little triangle wave. So you can see there 90 kilohertz there. So that's after the main inductors, so a little bit noisy. Obviously a subwoofer is never going to play or reproduce that, just a little bit of noise, no problem. And then I believe that's what this inductor is designed to kind of try and get rid of. So let's go after this inductor. Yeah, that's a fair bit less. You can see before that inductor we have triangle wave. After that inductor we have, it's a little sine wave almost. It's a little noisy sine wave. And that is only 280 millivolts. So yeah, for subwoofer application, absolutely no problem at all. And that's what we're going to see on the speaker terminals. If we go over here to the speaker terminals, we're going to probably see, yeah, exactly that waveform there. So yeah, no issues at all for subwoofer application. But if you did want to use this on tweeters, you obviously can't because it's a subwoofer amplifier and doesn't go that high. But if this exact Class D circuit was to be used in a full range amplifier, you would get a bit of background floor noise as a hiss on the tweeters. Alright, cool. What I want to do now is take the thermal imaging camera and I want to see how hot various different parts of the board are getting under kind of idle operation. So let's take the thermal imaging camera here. I need to turn on, I need to give some measurements here, some readings. Okay, oh, here we go. So we've got hot spot and cold spot, which is cool. That's what we want to see. So let's power the amplifier up again. Now the power supply MOSFETs, we shouldn't have any idle heat on these at all, especially given the low duty cycle, which we don't. As you can see here, 24.6 degrees Celsius, that is absolutely fine. We've had the amplifier on for a little while now. The transformers as well don't seem to have much idle loss, which is really good to see. We've got some hot resistors here, which is fine. These are the rail pull down resistors. So that's just going to cause the rail voltage to sink to ground when the amplifier turns off. Obviously, the rectifiers, there's no current passing through them, so they are stone cold as well. Good to see. The drivers as well, extremely chilly. There's so many drivers for such little number of MOSFETs that is understandable. Let's have a look and see what's going on over here. We have a couple of resistors there getting a little bit warm. But nothing too bad. We've got 50 degrees Celsius on those resistors there. They might be VCC supply resistors, perhaps, for example. Not too much of a problem. Now let's have a look at the PWM card. I'm going to put my little lens on here, which is going to make this macro lens. so we can get it right up nice and close at this PWM card. We've got a surface mount resistor there, which is reaching 52 degrees Celsius, not too much of a problem. Obviously with surface mount parts, you don't want them getting too hot because the constant heat and cool cycles does crack the lead-free solder over time. So that part there, yeah, not too bad. You know, if it was like 60 plus, I'd be worried, but 50 degrees Celsius, yeah, it's not too much of a worry. The CL494 doesn't really run very hot, that's cool. And not too much else here running very hot, which is nice to see. Excellent stuff. Yeah, that's pretty well optimized for this amplifier. Alright, let's move on to the output section now. Output MOSFETs do tend to run a bit warmer idle in many amplifiers due to cross conduction just from the drive circuit being poorly optimized, but in this case, absolutely beautiful. These output MOSFETs are stone cold, and they've been running for a little while now. Now they are still technically on the heatsink a little bit, so I'm just going to pull them away from the heatsink just so they're kind of like floating in midair for a minute. Let's get away from the heatsink there. So these are the low side, and then got the high side here as well. But that looked stone cold to me. Power up again. I'm going to go up to 14 volts on the power supply, which should enhance any cross conduction. But I mean, pretty much stone cold. I mean, we've got this one here just rising in temperature a tiny bit more than the others. Which you can see, what, 24 degrees Celsius on that one. Well, again, 24. So yeah, barely 25. So we're getting a tiny bit warmer on that one. But this is negligible. This is very, very nice. Very, very well optimized. Class D idling. Yeah, one of the FETs does get a bit hotter than the rest of them, but you're always going to get that because the VT is never going to be exactly the same for each MOSFET. So you're always going to have it when you're running MOSFETs in parallel like this. You're always going to have one of the FETs turn on ever so slightly sooner than the others, and that just causes a bit of cross conduction like this while that one's on first. But this is minimal. This is barely getting warm than the rest of them. Over here we can see we've got the auxiliary supply circuit and the resistors that are in line with that, current limiting resistors. Currently up at 48 degrees Celsius. That's absolutely fine. What's really interesting on the thermal imager here is you can see that one of the resistors is hotter than the other, and that's fine. That just shows that probably the 7812 is there's more components using the 12 volts than the negative 12 volt rail. So obviously a bit more current is being drawn through the positive 12 volt one. That's just something interesting. That's just not a problem. That's just something interesting for you to see and to bear in mind. These voltage regulators, obviously they're on the heatsink, but they are absolutely icy cold. Very, very nice. Not going to have any issues with heat and core cycles really there. Now comes the interesting part. Let's have a look at the output driver card. I want to see how well is this 2184 PDIP package dealing with driving all these output FETs directly. By the looks of things, pretty well. We've got 53 degrees Celsius on there, not too bad. However, you notice this transistor up here, currently idling at 74 degrees Celsius. Now, that in itself isn't an immediate problem. You know, the transistor will be within its spec here. However, bear in mind that this amplifier is just open on the bench in its ideal environment. We are not in a hot vehicle. It's not the middle of the summer, and the amplifier case is not hot from being played. So this transistor being already at like 75 degrees Celsius, give this the worst possible conditions and scenarios. This is going to be well over 100 degrees Celsius, which is not really ideal. It's stressful, means there'll be you know, heat and cool cycles, which may crack the solder over time or may shift the structure of the silicon die inside. So that's something to bear in mind. It'd be better if this component was a larger package. Ideally it'd be a through hole, but obviously it's on a surface mount built card, so you can't really do that. But that transistor would be better to be a larger package to dissipate the heat a bit better. We also have some resistors next to it which look like they're a little bit warm as well. We've got 66 degrees Celsius on some of these resistors here as well. So these would be better to be larger packaged to dissipate the heat a bit better. So that's something that I'll obviously mention. I like that with the thermal imager you can actually kind of see, if I turn the amplifier off now, you can kind of see the die structure inside the chip. So the amplifier is now off. If I power the amplifier back on now, when Class D switching initializes, you can see the little square of heat inside the chip getting warm, and that's where the die is, just over to the right a little bit in that package, which is really cool. I like that you can see that. But really, there's not much else on the driver card that gets warm much. You know, the 072C is not particularly hot. The driver, yeah, 52, that's fine. It's a nice big package. It's going to be able to dissipate some heat. That's absolutely fine. No issues there at all. No worries about that. What about on the main board? We got a resistor here, which is a little bit toasty, 75 degrees Celsius. I'll have a look at exactly what that's doing. I don't know off the top of my head what that one's doing, but that's a little bit warm. But this is just a regular through-hole resistor, so it's actually not going to be as susceptible to the kind of problems with heat and cool cycles as surface mount parts are. So yeah, there's no issues really with that being a bit toasty. That's going to be fine. Even if it was over 100 degrees Celsius, it's not really going to pose too much of a problem. That's absolutely fine. So let's just take the lens off and have a look at the rest of the output section here, see what else we've got going on. Nothing else in the drive circuit is like particularly hot, so quite well optimized, to be honest. And over here on the other side of the board, we've got a big resistor here getting warm. That's fine. That's just dealing with the high frequency energy. Okay, hang on a minute. Now these capacitors, these bipolar aluminium capacitors, they do run a little bit warm, don't they? It's really not ideal for aluminium capacitors to sort of generate any heat on their own like that. Aluminium capacitors like this really hate getting warm, really hate getting hot. Now I understand why they're using these here. In order to get rid of the Class D noise, it is ideal to run a combination of film capacitors and these big aluminium capacitors, just to kind of get the best of both worlds in terms of capacity and low ESR of the two combined. But they don't seem particularly happy here, and they are going to get even hotter if the amplifier is clipped, because there's going to be a lot more high frequency information generated when this amplifier is under clipping. So we're going to have a look at that shortly. Actually, we're going to clip the amplifier and see how hot they get. That might be a weak point that we might need to kind of maybe swap these capacitors out for some big film caps. Might actually be better. What I do like though is that the output inductors are running very cool at idle. It's not always a given. Sometimes the output inductors are not really particularly well spec'd for the circuit and they run very hot at idle, but not in this case. Nice and cool on the output inductors, which is good to see. The relay running warm, that's normal. We have a coil in there which is holding the contact open, so that's fine. We've got a little capacitor here, C202. That's kind of quite warm there. That is running up at 50 degrees Celsius. That's interesting. What about the one on the other side over here? Yeah, that's going to be dissipating some high frequency energy through that capacitor. Not a problem though. That is a little ceramic cap by the looks of it. So that's going to not really be too fussy about being hot, but just interesting to note. But yeah, overall, not too bad. Preamp circuit, yeah, the op amps just kind of very, very gradual amount of heat, so nothing too bad there either. All right, nice. So yeah, this is looking pretty good, to be fair. The only issue I've really seen is an overly hot couple of components on the output driver card. But as it goes, in terms of, you know, like, yeah, this has been on for like a good few minutes now. The output MOSFET's running nice and cool at idle. Output inductors nice and cool at idle, drive circuit fine, power supply drive circuit fine, no cross conduction on the power supply FETs. This is looking like a pretty well optimized amplifier off the bat in terms of idle operation. So that's really, really nice to see. Okay. Let's have a little read of some live chat now, shall we? The switching frequency with changing rev voltage is actually a good thing. That means the circuit will compensate for rail droop. Will it? Basically, the amp tries to keep the area under the square wave constant. With a lower gate voltage, it just takes longer for longer time to get the right amount of power into the inductor. Huh, okay, I understand. So maybe that is, I've always assumed that that is like a little bit of a janky thing. In terms of the gate voltage on the voltage on the gate, that doesn't change. The amount of gate voltage is the same from like 10 volts to 16 volts. But the actual voltage into the inductor, yeah, I kind of see what you're saying now. Interesting. Not all amplifiers do that. Like the modern amplifiers using the kind of 20957s and the SI 8244BB and stuff like that, they don't change the switching frequency with input voltage. And because those chips are more modern and kind of more refined, I assume that that would be how it should be. Maybe the big resistor should be further from the caps. Yeah, it's not ideal placement, I'll give them that. These rail pull-down resistors shouldn't really be that close to the rail caps, but these caps are pretty big, have a big thermal mass. I don't think that the heat from the resistor here is really going to affect these caps. Maybe if the amplifier was mounted on its side like that, where the heat can rise onto these caps, but they weren't getting drastically hot, like, they weren't like 80 degrees Celsius, so I don't think that that's too much of a problem, but in an ideal world, you'd space them a bit further away, I think, for sure. Ba, 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 ba. Okay, cool. So in terms of idle operation, we are all good in the hood. What I'm going to do is I'm just going to quickly have a look at my notes. I'm going to start jotting some of these things down before I forget them. So let's just grab my notes for this. Okay, here we go. New document. Let's paste this in. So, in regards to idle operation, pretty well optimized amplifier by the looks of things. Right, power supply switching behavior, losses and optimization. I'm just going to note down here that we could have a little more duty cycle on the power supply gate would be nice, but well optimized throughout. No cross conduction or ringing, spikes, etc. Protection circuit behavior, we're going to test that in a minute. Edge case behavior, we'll test that in a minute. Output section switching behavior, losses and optimization. Really well optimized, barely any cross conduction between parallel MOSFETs, driver running within operational temperature, a couple of surface mount components on the driver card, a little too hot. Current bottlenecks and unspec sections we'll check. Preamplifier behavior we'll check. Assembly weakness seems pretty well built. Well built, no board flex, no immediate signs of vibration weakness with high mass components. Okay, thermal management analysis will check that as well. Customer satisfaction. I think going by how this amplifier feels, it's really nice. Tiffany RCA's, nice feeling switch, and potentiometers feel nice and strong as well. Zero gauge I think there's 70 mil, but definitely zero gauge inputs. 2 sets of speaker output terminals, 2 RCA in, 2 RCA out. So yeah, in terms of how this looks and feels to use, I'd say that that's pretty good, and the mounting method is decent as well. We've got 4 bolts along each edge here, and it's pretty sturdy. So yeah, I think this will be nice. This will be nice to own and feel. Okay, cool. let us move on to the next test that I want to make then, which is going to be edge case behavior and protection circuit accuracy, etc. So what I want to check first is the low voltage and high voltage protection circuits. When do they kick in? So as you saw earlier, this power supply driver card, which I'll show you again on the little hat cam here, it does have a jumper here which is supposed to enable or disable 9 volt protection. So that's supposed to turn the amplifier off when the voltage drops below 9 volts on the power terminals. Or if you're competing and you are dropping below 9 volts, then you can turn that off and the amplifier will try to remain operational for as long as it possibly can before the auxiliary supply voltages are no longer high enough for the thing to work. So we're going to test both of those and see. It's currently set to on, so the protection is on at the moment, I believe. So it should protect at 9 volts. So let's probe the output switch wave here with the oscilloscope. Turn the amplifier on. We've got 12 volts going in at the moment. So nice Class D switching has built 2 amps idle current draw. So what we're going to do now is we're going to reduce the voltage here on the power supply until this disappears or the amplifier goes into protect. 10 volts, 9.5. So we're now at 9 volts. So below this, based on the jumper on the driver card, this should go into protect any minute now. Which it doesn't. We're still operational at 8.5 volts. Nothing in the circuit is unhappy. Class D switching still looks beautiful. The idle current hasn't increased, so you know everything's still kind of switching and operational as it's designed to. 8.4, 8.3, 8.2, 8.1. So what's gonna die first? Sometimes when an amplifier reaches a critical voltage point like this, you can have unintended behavior of the drive circuit which glitches and messes around and can actually kill the output FETs. So let's go down below 8.1 to 8 volts. Still, oh, there we go. Class D switching has disappeared. However, the amplifier is still not in protect. We have 1 amp idle current draw. We still have power supply. We still have power supply switching. So the amplifier is still operational. It's not in protect. The voltage is just too low for the output section to actually work. I assume that the 12 volts reference negative rail just isn't high enough anymore and the output driver has turned off. If we bring this up again a little bit above 8 volts, 8.1, now we have Class D switching come back. So 8.1 volts is the lowest voltage this amplifier wants to oscillate on. But what's really nice to see is that the way that this amplifier kind of breaks down and the way that the circuits kind of start to shut off is that the output driver, the drive IC of the output section, is the first thing that turns off, which is exactly what you want. What you don't want is you don't want the PWM generation circuit like the TL072C or any of the op amps or anything like that. You don't want any of those turning off first and the driver remaining on, because that's when you get all of this nonsense spiking and pulses and shit get sent to the output FETs, which can kill them. So it's nice that the driver turns off first. I doubt that that was intentional. I think that's just a happy byproduct of how the circuit's been put together. But that means that in terms of low voltage by itself isn't going to kill this amplifier. Okay, you heard it here first. If you run this thing down below 9 volts, the low voltage itself as a thing isn't going to kill this amp. Look, we're going below and above, below and above, below and above. Class D oscillation is stopping and starting perfectly every time with no glitching or funny behavior. It's absolutely fine. So low voltage is not going to kill this amplifier by itself. So that's pretty nice. Okay, how about on the high voltage side now? So obviously we've got going to go up to 12 volts. We've tested 14 volts already. Now this bench power supply currently goes up to 16 volts. If that's not high enough, I'll have to dig out the other power supply to get it up at a higher voltage. So let's keep increasing this now. 14 volts, 15, 16. Okay, so at 16.1 volts, we're still operational. So we don't know what the protection, the high voltage protection is, but hopefully the high voltage protection point is low enough that it doesn't cause there to be excessive voltage on these FETs. Now these output MOSFETs are only rated for 200 volts, okay? So we cannot have rail voltage that is greater than 200 volts peak to peak, okay? So what we're going to go ahead and do now is just measure the rail voltage, positive and negative rail here, without hopefully shorting out against the ground, because this is a little bit tricky. Let's just turn that off for a minute. Okay, let's get the second probe on. So I want to probe positive rail here and negative rail at the same time. Okay, there's positive rail and there's negative rail. Okie dokie. So powering back up. So with 12 volts, we have plus minus 75 volts. There or thereabouts. So let's continue. So obviously we want the high voltage protection to kick in before we get to plus minus 100 volts. Oh, there's plus minus 100. 100.8. Okay, so we are literally banging on the door of the output MOSFET voltage breakdown limit with the amplifier at 16 volts there. I don't know what the high voltage protection point is on this, because my supply only goes up to 16 volts. So we'll have to hook up the higher voltage supply that goes up to 30 volts just to kind of nudge it a bit higher and see where that high voltage protection point is. But looking at it at the moment, it's still operational at 16.1 volts, and the rail voltage was plus minus 200, which is literally the output MOSFET breakdown voltage. So that's not good. I wouldn't run this amplifier at 16 volts if I were you, as it stands, but I'd be curious to see what happens first. Do the output FETs explode first, or does the high voltage protection kick in first? I'd like to see. Yeah, low voltage doesn't kill amplifiers. Like in the past with discrete, and this is going back to discrete class D amplifiers were a mess, and low voltage definitely would cause some sketchy behavior in the class D switching and class D drive circuit, which could definitely kill the output FETs. However, in an IC driven class D circuit like this, no, low voltage by itself never kills an amplifier. What kills an amplifier always is overcurrent and potentially class D clipping, and as you drop the rail voltage, you just bring the clipping point much closer to the sine wave, so you're much more likely to clip when your voltage drops. You can be absolutely wanging on an amplifier at 9 volts, provided you're not clipping, the amplifier is very happy. And actually, because the potential inside the amplifier is less, there's less voltages, it'll actually last longer at 9 volts than it will at 14 volts, because firstly it's making less power, secondly the voltages inside are less, therefore the heat generated is less and the components are under less stress. So provided you're not clipping it, low voltage in an amplifier, absolutely no problem whatsoever. Okay, so we've found the low voltage. So 8.1 volts was the cutoff point there for the low voltage protection mode. Now, what about if we move this jumper? We have this jumper here, so if we go from 9, so the protection, the 9 volt protection should have been on, which it wasn't. So that is not ideal, is it? It looks like that the intention was for this amplifier to go into protect at 9 volts, but it didn't. So let's move the jumper over to the off position and just see if that makes any difference. Doubt it will, but I'm just kind of curious to see if it does. So let's power back up, class D switching. We're going to start at 10 volts here. Okay, let's go down from 10 volts. 8.9 volts. Or 9. Okay, 8.7. So we're still operational. So yeah. 8.0, so it makes absolutely no difference. So that jumper is just completely makes no difference. So yeah, there's obviously going to be a voltage divider, a couple of resistors, which that circuit is using to determine what voltage is on the terminals. Because obviously the amplifier doesn't read 12 volts from the power terminals. It'll be sent through a few resistors to like a few volts, like 1.2, 1.5 volts or something like that for the comparator here to measure. And obviously those resistor values are not calibrated properly for this amplifier circuit or something, because yeah, this jumper is doing absolutely nothing. So the voltages are obviously out of range. Okay, so we will find the high voltage protection point. However, given that we were already at the output MOSFET breakdown voltage, I'm going to do the high voltage protection point test last. I want to do every other test first because I don't want to kill the output VETs and have to replace them before I carry on with other testing. So I'll do the high voltage protection point test later on. Next, let's move on and have a look at so power switching behavior, protection circuit accuracy and behavior. Okay, so low voltage protection non-existent. Okay, edge case behavior. Reducing voltage below operational threshold results in no dangerous behavior. That's good. Okay. That's one note on there. So, protection circuit accuracy and behavior. So the other protection circuits that this is going to have is it's going to have, obviously we have low voltage, high voltage protection, we have overcurrent protection, which we will test. We have some shunt resistors on the board here and here, which should be measuring the amount of current across the resistor and shutting the amplifier down when it detects too much current across them, which we'll test. What other protection is it going to have? It's going to have thermal protection. So yeah, we can get the heatsink cooking up to temperature and see when it goes into protect. That's one test we'll do shortly as well. Maybe we'll do that one next. What else do we have? Other protection modes. DC offset protection. There's no real way of testing that without the amplifier being dead. I guess I could temporarily short one of the rails to the speaker terminals and see if it goes into protect, but it should do. Maybe I'll do that as one of the final tests as well, because I don't want to damage anything unnecessarily before I do some of these other tests. Edge case behavior, such as rapidly switching the amplifier on and off while at high output, battery voltage extremes, signal, main, ground, potential differences, etc. Okay, so what I'm going to do is, next test I'm going to do is very rapidly power the amplifier on and off. There have been Korean designs in the past that have had a design flaw where if you apply and remove and apply the remote in quick succession, it actually causes a glitch on the output drive circuit which kills the output MOSFETs. So I'm going to do that real quick just now. We're going to power the amplifier up with 12 volts going in. I've got class D switching. Now we're going to turn the amplifier off and then suddenly back on again. Off, on. Okay, so class D switching builds perfectly. There's no swing to negative rail or pulses or spikes or anything like that. The only thing I would note though, and bear in mind, is that if you do power the amplifier off and then immediately back on again, sometimes the relay engages before class D switching builds, which is obviously the wrong way around. You always want the relay to engage after class D switching has built, so you don't get a pop through the subs. But given the speed at which I'm doing this, like, let's do, okay, so I go off, on. Okay, that was before, off, on. Okay, that time, class D switching was before the relay, so that's good. Off, on. Okay, so in order to get the relay to come on first, you have to be really fast. Off, on. Yeah, the relay was like instantaneous there. Realistically, I don't think you're ever going to have a situation where the remote is off on like within like 0.2 of a second. So I don't really see that as an issue. It's great that we don't have any glitching or anything strange going on with class D. The muting circuit, which is designed to prevent class D switching from activating immediately. It's supposed to have like a little delay time. That's working beautifully. That's preventing any of these glitches or any of these weird behaviors from occurring. So that's really good. Love to see that. Let's just make sure that that is the exact same behavior at voltage extremes. So let's go down to 8.5 volts and make sure that's exactly the same behavior. Oh, the relay takes ages to kick in at 8 volts. Off, on. Off, on. Off, on. So everything just takes longer at 8.5 volts. But that's understandable. You never be running it that low anyway. Let's try at 14 volts. Off, on. Off, on. Yep, beautiful. This is very well optimized, perfect operation here, really, really nice. So that's really good. Okay, excellent. So let's make a note of that. Rapid on-off does not cause any glitches or issues of note at voltage extremes. Okay. Next one I want to do is connect up a sub and power the amplifier on and off quickly while there is like high output signal being played, just to see whether it kind of breaks up while it's playing an audio signal at all like that. Output section switching behavior, losses and optimizations, that's good. Oh, we need to test current bottlenecks and under-spec sections. We'll do that when we hook up the big power supply. Preamplifier behavior and filter accuracy. We can have a look at that actually before we connect a speaker. So let's grab an RCA wire. Let's plug that into the side real quick. Input, and yep, let's get a flathead screwdriver. I never have a flathead when I need a flathead. Here we go. Okay, so everything at minimum to start with. I got some signal going in, so let's turn the signal generator on. Let's go down to 12 volts. Okay. So everything's at minimum. We have low pass filter at 35 Hertz, which is the minimum set on the side. Gain and subsonic is also at minimum. Very nice. Let's go ahead and probe the speaker output, which is going to be this one. Have a look at the sine wave on the oscilloscope and adjust the frequency and see whether these filter markings are accurate or not. All right. Reject high frequency. Okay. So there's a little bit of sine wave. So I'm going to calibrate up to sort of 14 volts RMS there. There or thereabouts, 14 volts RMS. So we've got 28 Hertz going in at the moment. So if I go reduce further all the way down to 20, there's 20 Hertz. 14.5. Okay, so with the low pass filter on minimum, we have the highest amplitude at about 22 Hertz. Yeah, 20 to 22 Hertz we have the highest amplitude. Then increasing all the way up to 30 Hertz, we have a tiny reduction in amplitude. We're down at 12 volts now. And then up to 35 Hertz, we are at 10.6 volts. So yeah, from 20 to 35 Hertz, we've gone from 14.5 to 10.1 volts there. And then by the time we're at 40 Hertz, we're at 6.3 volts. So the biggest reduction in output is going to be from about 35 to 40, there's like quite a sharp reduction in output. And then by the time we get to 60 Hertz, we're down at 1.6, so barely any output at all. Okay. So yeah, that's pretty much what I'd expect. That's going to be like a 12 dB roll off, I think. And you're going to obviously have that impacting and affecting the lower frequencies as well. Now in terms of the subsonic filter, let's go down and check the subsonic filter. So we have 22 Hertz at the moment, up at 14 volts RMS. Let's reduce this and see where the signal starts attenuating. Okay, so we're now down at 12.8, and that is with 15 Hertz. The marking on the side is 10 Hertz for the lowest point on the subsonic filter. By the time we get to 10 Hertz, we're at 6.9 volts. So yeah, we've like less than halved, so that's probably about right. And then by the time we're at 5 Hertz, we're, yeah, 1.6 volts, yeah, barely anything at all. So yeah, that's working pretty much as you'd expect. Excellent stuff. Now let's increase the low pass filter all the way to, well, let's put it on let's put it on 250 Hertz. So that's all the way up. So I've increased the low pass filter all the way up to 250 Hertz now. Okay. So we shouldn't have any change in the signal until we probably get to around like 180 Hertz, something like that. So we've got 10.3 volts, keep going up. Okay, so we don't get any change in the signal until we get to 164, and then we just start gradually tapering off a little bit. By the time we're at 250, we're down at 7.9. So yeah, it's a little shallower, I think, on the low pass filter rolling off on the higher frequencies. But yeah, it is kicking in pretty much where you'd expect. So yeah, that is pretty nice. Like to see it. Now in terms of the gain knob on the side says that it accepts up to 8 volts RMS worth of signal strength. So my signal generator here, if I just probe the RCA, my signal generator here can output a maximum of, what can it do? 7.3 volts RMS worth of signal strength. So I'm not actually going to be able to probably clip the preamp circuit in this amplifier, but we'll be able to go up to 7.5 volts and see what, just make sure that we don't get any wave shape change or anything like that. So the gain is on minimum just now. So we should get pretty close to clipping with 7.3 volts. We shouldn't reach clipping, okay? So I shouldn't be able to reach clip point with 7.3 volts worth of input. If I do, then it means that that marking on the side is inaccurate. So let's go ahead and probe the speaker terminal, and let's power up again. All right. So if I increase all the way, yep, as you can see, we're not clipping yet. I have my signal generator at maximum, so that's 7.3 volts worth of signal going in, and we are not clipping the amplifier. So that probably is accurate at 8 volts. So let's turn the gain up to, now, the gain maximum is 0.2 volts. So let's calibrate at 0.2 volts RMS on my signal generator. That's going to be 200 millivolts, which is pretty much here. 200 millivolts, that's right about there. So we should pretty much reach amplifier clip point when I turn the gain up to full at that amount of input signal. So let's probe the speaker terminal again. Let's go up to 20 volts divide per division. Here we go, coming up. Okay, we're not quite clipping. So how much extra, and that's at 12 volts as well. So how much extra signal do we need to reach clip point? I'm just increasing the signal gradually until we reach clip point. Okay, there's our clip point. So how much signal was that required? Now actually what's interesting is I've only got one RCA going in actually. That's a good point. I've only got one RCA going in, and obviously with two maybe that would be different. So with one RCA going in we have 0.31 volts in order to reach clipping at 12 volts, and it would be more at 14 volts because the rail voltage is higher. But with both RCAs it's probably going to be a bit higher, but that's looking like it's pretty much within what it's supposed to be on the markings there. It's pretty accurate. Now let's check the accuracy of the clip LED. Is the clip LED accurate? Let's have a look. So let's grab the hat cam, plug the RCA back in. Turn the gain up a little bit. So we have our clip LED just here. 12 volts going in. Probe the speaker terminal. So let's see how accurate is that clip light. Okay, so the clip light actually comes on a little early. So the clip light is starting to flicker here, but the sine wave is still very clean. The sine wave starts clipping about here. That's a little bit of soft clip, and the clip LED is solidly on at this point. And I know it looks like it's flickering on the camera, but in real life that is solid. So it's a little bit early. I'm just going to make this oscilloscope screen a little bit bigger for you. Yeah, we get a reasonable extra amount of sine wave there before we reach the clip point. So it's a little bit early. Let's see if that's the case with a lower voltage. Maybe it's not quite comparing properly. Yeah, it's a little bit early at 10 volts as well, about 14. Touch early there as well. So if anything, it's a touch early. I mean, I guess it's better than being a touch late, but it does mean that you might be leaving like 100 watts or so on the table if you're setting this to exactly when the clip point starts coming on. Yeah, a little bit early, but that's fine. Better than being tons late. Whew. What happened to your mic clipping a lot now? Is it still clipping? 1 2 1 2 1 2. Ah, doesn't seem to be clipping. I thought you typically ignored a flickering clip light. Oh, I guess it depends on the user. There's no like, if it doesn't say that in the instruction manual, if there's no kind of typical thing. Like for me, I would always go by when the clip light starts flickering, you're like touching the rail. That's how I would I'd do it. Okay, cool. So yeah, the preamp settings do seem to be very accurate, and they're set up for, you know, for this amplifier to sound really nice and smooth on a subwoofer application. All right, next thing that I want to test then, we're going to start getting onto some actual power testing and some current draws soon. Thermal management analysis, assembly weakness, preamplifier filter. Let's just make a note of this. Filters are accurate. And gain markings accurate. Comma. No distortion at different filter points. So that's pretty nice. Okay, so now I want to move on to, I want to connect a speaker and just see what this is like through a sub, powering on and off quickly and stuff like that. So we're going to hook up a nice old sub here. This is a Sony Explode, the kind of vortex cone model, the 1300 watt. This is nice. This is a nice old driver, this. So yeah, let's just flip this over, hook up this sub. Yep. Okay. So what we're going to do now is connect up an RCA here and get some signal going into this sub, and we're going to power the amplifier on and off just to see whether the sub remains clean sounding during the on-off phase of the amplifier here as well. So let's do low frequency, like 25 Hertz here, power up. Very nice. Okay, power off, power on, off, on. Yeah, very nice. No issues there at all. Excellent. Let's just have a look with the old thermal camera Ruby. Thermal camera has frozen. Oh no, it's just like mega glitchy. So this is what I was telling them about. After the thermal camera has been running for a while, the software just like freezes and crashes. Look at this. So this is the Windows software. So the only drawback I have with this camera is the Windows software is very, very bad. I suspect it's got like a floating point number leak or something, or like a memory leak or something. But yeah, the Windows software just crashes after it's been open for more than like 10 minutes or so. I have to go in and start this up again for it to actually work. There we go. And then I have to go and set the bloody, it doesn't remember the settings that you've set either, which is annoying. 90 degrees, rotate, there we go. Okay, so yeah, I just wanted to have a quick look at the thermals on here. So yeah, these caps here definitely run warm, which is not the most ideal thing in the world. Okay, what I want to do real quick is I want to disconnect the subwoofer for a moment, and I want to clip the amplifier quite hard and just see what parts on the output section get stressed or hot as a result of the amplifier being clipped. I want to see if the output MOSFETs heat up. I want to see if any of the filter capacitors on the output section heat up when the amplifier is being clipped. I also want to see, because some amplifiers will actually kind of soft clip. They won't let the sine wave touch the rail voltage per se. They will sort of clip a bit before, like in the preamp circuit, for example. So let's just zoom out from here and let's turn this back on. 10 volts going in. Power up. Okay, so we do hard clip, we do touch the rail, as you can see on here. Yeah, we are touching the rail. Now let's grab the thermal imaging camera and let's see whether anything immediately starts to get hot while the amplifier is clipping. Okay, the output MOSFETs, they do not really care. They do not get hot while the amplifier is clipping. How about these capacitors? They're not like quickly heating up, but they are running warm. How about anything on the drive circuit? If we clip the amplifier, does anything like sort of immediately start to get hot over here? No, not that I can see. Yeah, pretty cool. The amp doesn't really seem to care about clipping too much. Nothing like immediately kind of starts getting cooked while it is clipping. So that's kind of cool. Output FETs don't really care. Nice. Very nice. Alright. Now I want to move on to some current analysis. I want to see how current flows through this amplifier and what bits get hot where, etc. So in order to do that, we need to connect a resistive load to the output terminals of the amplifier, and I also need to remove the these things from the heatsink because I want to see what parts get hot when current is drawn. I want to see what heats up first. So let's remove all of these clamps, and that will then allow us to see the component heat. So since I changed the ads to conservative, how has the adverts been for everyone? Have you been getting any ads? Have they been annoying? Or have you not got any at all since I changed it to conservative? Let me know. Is this a good amp? It says quad feed. So far, it's actually shaping up to be pretty awesome. Not gonna lie. Shaping up to be pretty damn good so far. Okay, so I've just pulled all of the power passing components away from the heatsink, and that will let us see what gets hot first when current is passing through the board. I'm going to tighten up these terminal connections a little bit just so that we have a decent connection on the terminal. Okay, nice. Now I'm going to hook up a resistive load to the amplifier. I'm going to connect 2 ohms to start with. I suspect this amp is like a few thousand watts RMS. I haven't actually looked up how much power this thing is rated for. $2.8K. Okay. I mean, this thing's freaking massive for a 2.8K. I bet it's expensive as well. How much does this cost? Personally, if I was recommending this amplifier to somebody, I would be recommending they run it at 0.5. 600! Jesus! Okay. Well, there'll be a lot of people in the chain between the factory and the end user for that. So there's going to be some profits, you know, along the way to account for that amount of money. It's understandable with these kind of brands. It is so far this is shaping up to be a really nice amplifier in terms of circuit optimization, operation, etc. You know how it's working. Balancing between parts, circuit areas, etc. But my God, that is quite a lot of money. But money no object, if you were looking for a 2.8K, this would probably be the one I'd recommend based on what I've seen so far. Okay, cool. Let's put the thermal imager up here. It's not rivaling Zapco. Well, this is better than the Zapco amplifier that I looked at. I'd buy this over the Zapco anytime. Zapco are rubbish. Okay, right. So we have the resistive load hooked up. We're going to turn the power supply back on. 12 volts going in. Let's turn the gain down a little bit. Fantastic. Oh, okay, that was a joke. No worries. Okay, let's power this back up and let's start drawing some current, and I want to see which components get hot first. We can make some bets if you like. Going by what I see here, I suspect it's probably going to be the output FETs. I think the output FETs are going to be the thing that are the current bottleneck, followed by the power supply FETs, and I think the rectifiers are going to be staying coolest for longest. So let's power it up and see. Okie dokie, 2.2 amps. So let's start increasing the sine wave. Oh, it helps if I plug in the RCA, doesn't it? Helps if I plug in the bloody RCA. Okay, let's try that again. Okay, there we've got some current. We've got some current now. So, if I'm just let's just turn that up a little bit. So yeah, about 4 amps here. Okay, so in terms of the amplifier under load, yeah, the output FETs are definitely the bottleneck here, and the heat isn't even between them either. So let's have a look at the rectifiers cold, power supply cold, power supply cold. That's hot because it's a voltage regulator, so just ignore that one. But in terms of output section, it is definitely the output FETs which are the thing that are the bottleneck, and it's not super even either. I'm just gonna quickly like dump a bunch of current in here, and you'll see these probably get hot real fast. Yeah, so we're at 40 degrees now. So what have we got after that little burst of current? We've got 54 degrees on that one. Over this side, 45, 57. Yeah. So in this instance, right, the power supply section is absolutely overkill for the output section. All right. So that $600 that you're paying for this amplifier, and for this amplifier to obviously exist, right? This power supply section could definitely support probably up to like 4K, maybe even 5K with the rectifiers like that. But this output section is going to be what's limiting you. Now, this is quite a lot. These output FETs are pretty good. What have we got? 1, 2, 3, 4, 5, 6. So I'm just thinking about another amplifier that uses these output FETs. Okay, these 52N20s. We've got the JBL GTO 14001. That uses 8 of these output MOSFETs. From what I remember, yeah, it uses 8 of them. And that thing benches 2K all day long. No stress. Absolutely awesome. And you can even get it to do more than that. So 8 of these FETs, 2K all day long. How many have we got here? 3, 6, 9, 12. We've got 12 of them here. And this thing's only asking or rated for 2.8K. Going by what I know these FETs are capable of, and these FETs are also used in the B2 MA6000. How many of those are used in that? Let's have a look. Let's grab a picture online of the B2 MA6000.1. Images. We have 4, 8, 12, 16. Right, so this B2. This is a 6 kilowatt amplifier, and it uses 16 of these FETs. And this is a 2.8 kilowatt amplifier that uses 12 of them. So 2.8 kilowatts is not very much power for the components that are on this board. So I would, if I was the manufacturer for this amplifier, based on all of the components here and their ratings, I would be giving this amplifier a 0.5 ohm rating under warranty for sure. Based on this maybe making 2.8K, at 0.5 this should be able to make definitely 5K. So I would be probably rating this around 4.5 to 5K at 0.5. That then makes the $600 price tag a lot more appealing. Running this thing at 1 ohm at 2.8K is gonna be barely tickling anything in here really. And you know, if Synergy wanted to warranty this at 0.5 without making any drastic changes, there's plenty of space here along the heatsink on the output section. All you need to do is replace these output MOSFETs with some larger packaged TO247AC components. I can't think of any. So yeah, maybe some 300 volt, maybe like some 38. No, the 38 N30s wouldn't quite be enough. Maybe some what have we got? 300 volt parts. So yeah, I'd probably go for some 300. So either 200 or some 300 volt parts that are like, yeah, in the region of 50 to 60 amps each. And you could easily fit 6 per side like you've got here. It'd be a little bit extra manufacturing costs. Yes, the effects will be a bit more expensive, but the layout is already done. Everything else is perfect. The drive circuit will be able to handle it. And then all of a sudden, you've got an amplifier that is absolutely all day long stable at 0.5, probably for about 5K. Yes, exactly. The output MOSFETs, the voltage threshold seems to be a bit close, so we're going to be testing that afterwards. But yeah, in terms of where the bottleneck is in the amplifier in terms of thermal management, it is in the output FETs here. They kind of heat up pretty quick here. So what I would suggest, if they were going to make any changes, would be swap these output FETs for some larger packaged TO247AC parts, just so that they have better thermal transferability to the heatsink, and then all day long the rest of the circuit and everything else here will definitely be able to handle a 0.5 ohm warranted rating. Yeah, absolutely all day long. But yeah, the output FETs here as well. I don't know if you noticed on the thermal imager, the heating wasn't super balanced either. So some of these FETs are definitely doing more power than their neighbors. I'm going to power it up again here so you can see. Okay, so powered up again. So if I increase the signal now here, did I remove the RCA? That was silly. So some of these MOSFETs are definitely doing more power than the ones next to them. Seems like these middle two here don't take really as much of the power, and that can be a difference in VT and also a difference in RDS. Obviously, if the VT is lower, the FETs with the lower VT will turn on sooner, so therefore they'll be contributing a bit more of the power because they're on for longer. But also, if the RDS is a little bit lower of some of these FETs, then they'll get hotter quicker. So yeah, if this amplifier was abused and used, you know, at its current limits, these FETs that are getting hot would definitely be the ones to fail first. And over the other side, is actually a little bit more even. Like, there is definitely some heating differences, but it's not as pronounced as over on this side. These ones in the middle here, these aren't really contributing much at all to the output. And this is the problem when you have parallel MOSFETs. In an ideal world, you just have one high side MOSFET and one low side MOSFET, and then you don't have this issue of power imbalance between MOSFETs. And you know, in some cases, some of the MOSFETs that are there aren't actually doing anything, barely at all, and you know, not really contributing much to the power. So yeah, interesting. Okay, let me make a note of this. So current bottlenecks and unspec sections. Output section. Output section is the source of the heat. Full stop. Output MOSFETs. Man, that does not like that. Output MOSFETs would benefit from being larger package to dissipate the heat more effectively. Full stop. Power supply and rectification circuit is drastically overspec'd. For the amplifier's rated power. Full stop. Output section is also a little overspec'd for 2.8K, comma, the components here could manage about 4.5K, no problems. Given enough rail voltage. Current sharing between output MOSFETs is not ideal, but not critical. You could probably mitigate a lot of this current sharing problem with the output FETs by reducing the gate resistor value, because that will then mean that the FETs spend less time in that kind of transitional stage between being off and on, and so the ones that have a lower VT won't be on for much longer than the other ones that have a higher VT, because the gate resistor is lower, so therefore the turn on kind of switch on phase is much faster. So that might be something to recommend, is slightly lower value gate resistors on the output section, which might help to improve the current sharing between the output FETs. That's something that I can actually try. I could try fitting some lower gate resistors and then doing this current, you know, this power test again, just to see if the MOSFETs all heat up a bit more evenly. Right, what else do we have? So power supply, that's fine. Protection circuit. So we need to check the overcurrent protection, and we need to check the high voltage protection point. Upper section switching behavior, current bottlenecks, underspec sections, preamplifier. Thermal management analysis. Yeah, I need to check the thermal protection point as well. All right, so that's what we'll do next. I'm going to put all of these clamps back in place for the MOSFETs, and we're going to hook up the big Taramps power supply, and we're going to see where the thermal protection point kicks in. So are you doing consulting for Synergy? Yes, kind of. This was sent to me by Synergy to analyze this current circuit layout to see whether there were any immediate problems or drawbacks that needed to be addressed. So yeah, I'm obviously currently assembling a report of all my findings that will go back to them, and then any changes that they want to implement they can. But honestly, so far I'm not seeing anything drastically terrible. Everything seems pretty good. Like this is actually shaping up to be an amplifier that I might even recommend if it wasn't $600. Just based on the circuit itself, I'd be like, yeah man, this is pretty awesome. Or if somebody was wanting like around 4.5, 5k at 0.5, I'd recommend this. This will do absolutely fine. The problem is yes, this is a very well built amplifier, but it is over-spec'd. Like it doesn't. Like this amplifier could be much smaller. It could have half the power supply. It could have half the rectifier circuit, and it could have like less output MOSFETs, and still deliver 2.8K into 1 ohm reliably for many years without overheating and while sounding fantastic. It is overbuilt, and that obviously makes it be more expensive for no real benefit to the end user that I can see at this point, unless it was being used at 0.5. What I am tempted to do is I am thinking I'm going to do some modifications to this. We're going to fit some different output MOSFETs and potentially, well, what's the rail capacitor value? The rail caps are only 100 volts, so I can't, you know, I could increase the rail voltage, but it would be a bit of a pain in the ass because I'd have to rewind these 4 transformers. I think it would be better to make some modifications to this to really nail in its stability at 0.5, and then this would be like relatively decent in terms of what it can offer for the money. You know what I'm tempted to do actually, once I've finished this, so in my workshop, I currently don't have like a massive bank of lithium or anything like that to do huge power tests, all right? So what I'm tempted to do is to see what this will actually make in its current form at 0.5, I'm tempted to send this down to SineWave02, who does have massive lithium bank in his room and big power supply, to bench test this at 1 ohm and then at 0.5 to see what it is currently capable of at 0.5 and go from there. Your mic is clipping at the higher notes. Okay, let me adjust my filters. Okay, I've turned the mic volume down. If I speak loudly, is that still clipping? Just at a lower volume. Because if it's still clipping, then it's clipping the input rather than the OBS slider. And there's not much I can do about that. It's still clipping? So yeah, can anyone have a quick look on YouTube and see if there's any amp dynos of this video? Sorry, of this amplifier. 2800 certified. Is that from an amp dyno? Like, based on the rail voltage, what should this be able to do? Okay, 3300 at 1 ohm uncertified and 2800 certified. Interesting. Okay. Alright, cool. So all of the clamps are back on. So now what I want to do is hook up the big Taramps supply, I think, and start getting some heat into this thing. Now the Taramps supply can do, it's a 200 amp, so it can do 200 amps or 280 on a burst. So should do 3K at 2 ohm, huh? Right. Okay, let me just get this hooked up. I've got the my little plug adapters downstairs, so I'm just going to go and grab my extension lead for the Taramps smart charger. And I want to get this heatsink up to temperature. I'm going to connect a 1 ohm load as well now. Sam, what are your thoughts on the WFO Synergy? That's what I've got on the bench here, bro. I've just spent the last 2 hours going over my thoughts on them so far. $3,500 watts burst in 1 ohm. Okay, cool. Yeah, janky. It's fine. Doesn't need to look nice. Just needs to be a solid connection. Yeah, so these cables that I got from the loft were just a temporary thing for another test I did a while ago. What was I testing? I tested the I tested something on stream. Oh yeah, I tested that that Fusion Jomo Lomu or whatever it was. That's why the cables are kind of looking a bit janky like this. I think the Taramps has even smaller terminals, so that's going to be fun. Need a bigger bench. Yeah, so the Taramps has a very small output terminals. Very frustrating. I do have a big bank of ultra capacitors actually. So what I should do is I should just run a very short run of thinner cable from this power supply to my ultra caps, and then run some big cable from the caps to the amp. That is what I should do. Right, so this is 12 volts, which is on this one. And this is the ground, the negative terminal, which is on the other side. And yeah, this one I've had to really bend away all of these strands just temporarily to get this to go in. Did you ever get them sodium batteries? No, apparently they're still on a boat somewhere, but I think they've been lost, or I don't think they're arriving. I might have to claim a refund through AliExpress because I haven't got anything turned up yet. The problem is on the AliExpress website it says delivered, but then when you check the tracking it shows it's at sea. So it's kind of frustrating that they do that. It's like, no, it hasn't bloody been delivered. Shut up. Okay. Looks jank, but that'll work fine. Okay. Is the negative here connected to the negative of the main ground here when I plug it in? Right. Remote on the foot pedal. RCA going in over here. Yep, definitely need a bigger bench. Running out of space. The Taramp's power supply is not super quiet. It is a bit noisy. The fans are quite loud. Right, I need to go and grab my extension lead, so just bear with me for a minute, guys. So the reason I've got this big extension lead, guys, the reason I've got this big extension lead is because all of the plug sockets in the workshop are currently running on like multi-gang extension leads, and I don't want to plug this Taramp's charger into a multi-gang extension lead that's being used by other stuff. I want it to have its own plug somewhere, but in the workshop ones are all taken up, so I'm trying to run the power supply from a different plug socket elsewhere in the house, but it's not quite long enough at the minute. So let me just have a think. Where can I plug it in? Okay, so I don't have an immediate solution for that I can just quickly do on stream. So I won't be bench testing this to full power just now, because I don't trust the electrical mains wiring setup in the workshop currently to not have a big fit doing that. So what I'm going to do though is I'm going to just run enough power to this so that the heatsink gets nice and hot, so we can see where the thermal protection kicks in, etc. So that's what we'll do, just like maybe like 1.5k, something like that, and go from there. So if I probe the positive speaker terminal over here, let's have a look at the sine wave output from the amplifier. And obviously we've got some signal going in as well. And then turn on the power supply. So check, yeah, everything's hooked up. So we turn on the power supply just now. There we go. So now I'm going to hit the power button on the supply. Okay, fantastic. That's now up and running. So I'm just going to shove my multimeter probes into the power wires here, just so I've got a voltage readout, because the screen on my Taramps one is broken, long story. So we've got 12.6 volts, no worries, that's fine. I'm going to keep it down at 12 volts. And we're on full power mode as well, which is cool. So now I can power the amplifier up. We're going to use the thermal imaging camera, provided this... Nope, see, it's frozen again. See, Windows software, after some time, freezes. And is that because of a memory runaway? Nope, doesn't seem to be. It's a CPU runaway. Look at this screen. Right, look at this task manager. So temp master, 33% CPU not responding. Really frustrating. And when it is working fine and has not crashed, it currently sits at 2.8% CPU. So it obviously has some kind of runaway where it uses a bunch of CPU and crashes after being in operation for some time. Very frustrating, no worries. Right, so let's power the amplifier up and let's start hitting it with some load into 1 ohm and go from there. Okay, amplifier's up and running, got some signal going in. There you go. Alright, let's turn the thermal imager on and let's have a look at what gets hot. So here's my big stack of resistors. So I've no idea how much power we're drawing at the moment, because like I say, the screen on the power supply is toast. But in terms of thermal, we'll just wait for this to get hot and then see when the thermal management kicks in. Definitely doing a few thousand watts right now. The power supply is starting to warm up. And as you can see, as I predicted from the earlier analysis, the thing that gets hot first is the output section. See that? Power supply, dead stone cold. Output section is where the heat is generated. So there, we definitely need some lower RDS parts or something in order to make this more balanced. Either that or just less power supply, like save some money, smaller power supply for this level of output section, be fine. Do the dummy loads get warm to the touch? Yeah, absolutely. These things get pretty hot under use. Ah, the WFO is rated at 12.6. Okay, fair enough. See, it's obviously going to do more at 14 volts. So yeah, this heatsink just needs to wait a while to get warm, doesn't it? Obviously, there's like big thermal mass here, so one way we could speed this up would just be to blast it with the hot air gun. Nah, so I'm not going to clip it because, like I said, my Taramps power supply is not connected to its own plug. It's connecting through a ring main, like through a extension lead. So I don't want to draw like tons and tons of power through the mains electrical. Yeah, I guess I just wanted to see how this would like behave under under load. So I'm going to grab the heat gun now. And I'm just going to blast the heatsink with some good old hot air. And yeah, that will get this this thing cooked up nice and quick. Move these cables out of the way for a minute so these don't melt. is going to take ages, man. It's a big old heatsink. Right, heatsink currently at 60 something degrees. Yeah, so the temp sensor is literally right here. I'm trying to heat the point where the temp sensors are. All right, let's power the thing back up now, and yeah, let's just see whether we can get it cooked up any better. All right, heatsink currently at 70 something. Yeah, about 70 degrees on the heatsink, which is very, very hot to the touch. Like you can't keep your hand on that. It's uncomfortable. All right, so amplifier's coming back on. Oh, it's in protect. Yo, we did it. It's in protect. We did it, guys. So let's now start to cool off the heatsink until it's no longer in protect. Check this out. Right. Oh, hat cam. Did I kill the hat cam? Fuck. Hang on a minute. Hat cam. OBS has crashed. Right, can you guys still hear me? OBS has crashed. Ah, shit. Okay, so you can still hear me. So OBS is still streaming. Unfortunately, I'm unable to change scene. And the hat cam. You'll have to trust me. Right. Okay. So although you can't see the screen, I'm gonna bring up the thermal camera on my own monitor here. Okay. So the heatsink is currently at 68 degrees Celsius. We were in Protect at 70. So I'm just gonna try and power it up again. Okay. Now we're with a green light. So it seems that the thermal protection, kicks in at about 70. So I'm just going to turn the amplifier off again and heat it a bit more. So we're just heating it a bit more now to try and get it back into Protect. Come on. Okay, heatsink is currently at, oh, we're up at 82 degrees now actually. Okay, let's keep going. Okay, there we go, there's protection. Okay, so the heatsink protection point is 83 degrees Celsius. There you go, aren't you glad you waited for that? Right, let's turn the power supply off now. There we go. So, I mean, 80 degrees Celsius is definitely a bit too hot for you to be touching, but yeah, that's a pretty decent protection point, I'd say. Not bad, love to see it. OBS is still crashed, so guys, thank you very much for joining me on this stream. That's all we've got time for today, because I've got to reset OBS and that's a headache. I've also got other things to do just now. So hopefully you found this enjoyable and interesting. And hopefully, can you still hear me? Can you still hear me? I've no idea. I've even no idea if you can even still hear me. Hopefully you can. But yeah, hopefully you've enjoyed that and it was entertaining. And I will polish up a report on this and do some other testing on it. And it'd be really fun to make some modifications to this amplifier, like I suggested, with some TO247AC components on the output section, and make this 0.5 ohm stable, very stable, because that is my recommendation going forward for this brand, is to actually give this a 0.5 ohm rating, because yeah, it's super overbuilt in everything other than the output FETs. So a little modification there, and this should be good to go. So guys, enjoy the rest of your day. I'll catch you next time. Bye bye.